Our next speaker, Dr. Michael Silevitch. Hello. He is the Robert D. Black Professor and Distinguished Professor in the Department of Electrical and Computer Engineering at Northeastern. Good to see you, Michael. Turn it over to you.
Thank you very much. Let me share the screen. Okay. Can everyone see this?
Yes, I can see your slides.
Very good. So what I'm going to focus on is what I call "so what, who cares?" In other words, we've heard a lot about, the in-depth study of, innovative and impactful technologies. What I'd like to do is provide my perspective of what I've learned as a result of directing an ERC and how that shaped what I've done since that time. So, the basic point is that ERCs have pioneered this three-level approach, and I'm going to go into that. But the key is identify right up front, who cares? So what? What are we doing this for? What is the impact of what we're trying to do? What's your vision? Why is it compelling? What are the grand challenges? Why can't it be done now? And so the three-level approach that Lynn Preston really pioneered and really created as a mantra of the engineering research centers is what I'd really like everyone to engage with and focus on, because for me, this is a disruptive way of thinking about integrative, transformative, systemic technology development. So in a nutshell, what is the three-level approach? The first idea is at the system level, what is your vision? Who cares? So what? What is so important about this vision? Then what are the barriers that you need to overcome in order to achieve the vision? And how do you create the research thrust to address the barriers? You have to integrate those thrusts. You have to create test beds to validate the research, and then, to demonstrate that, in fact, you can reach your system goal with real-world applications to validate the vision. That's essentially the three-level approach. The ERCs themselves are the vehicle for transformative impact. We've heard that over and over again in this symposium. They're similar to a small company. There's really, in order to compete and win, you're talking about a 2% success rate. So you really have to know your mission. You have to have your vision. It has to be very clear. And as you see, each ERC has to have these elements in order to really be an impactful research program. And the key is a 10-year transformative research program. So to give an example of our ERC, Census, the Center for Subsurface Sensing and Imaging Systems, this is what I'm calling a process center. The system level goal is to develop tools that allow us to probe hidden regions, unexplored regions. And the whole idea is look at a gamut of unexplored regions and see if you can come up with a unifying way of attacking the exploration of those regions, so that when you come to the next hidden region, you're not reinventing the wheel every time you do a new exploration. So in our case, we're looking from the biology end at the nanometer to micron scale, looking inside of cells, looking inside the human body, looking under the ground, looking under the water. These are the ideas that we're exploring in our center. What makes it different is that the way that you explore the different regions is quite, different for the different regions. So with biology, you're looking with, let's say, optical probes. With the body, ultrasound. This is very, simplistic. Underground radar, and underwater sonar. And clearly there are multi-sensors that go for each of these regions. But the idea is that the sensors are different. The tools are the same. That was the underlying vision of what drove our center. So in that case, how does the three-level diagram evolve? So the idea is we want to have the system level goal of creating the process of diverse problems, similar solutions, as it relates to probing unexplored regions, subsurface regions. And that was a key enabling concept, that what do you mean by a surface and what do you mean by subsurface? A surface is a boundary separating what you can see and understand from what you can't see and don't understand. So the idea of probing subsurface means that you're going beneath the barrier and you're really looking at the unknown. It's not subsurface for the ground. That was a big fight that I had with my researchers. They said subsurface is only beneath the ground. I said, no, it's beneath anything that you know to where you don't know. It's a boundary. So the idea is, what are the barriers? What is the research thrust? And again, this is the same structure. So what did we do in our center? At the system level, we're looking at biomedical and environmental civil applications. At the testbed level, I'll come into a little bit more on that, but we're looking at validating environments where we could prove the principle of diverse problems, similar solutions. And at the fundamental science level, you can see three interlocking thrusts. The first one, to understand how to model the subsurface hidden regions. And the second is, how do you get signals in and out of those regions so that you can extract intelligence? And the third is, how do you manage the deluge of data, image and information data that's coming out of your ability to probe these regions? So here are the four validating test beds that we created. One at the biological level, it's a fusion microscope that allows you to look at cellular structures with many different microscopic modalities. A medical test bed, which is essentially an underwater, a tank of basically water with targets in them. The soil bed, which is a sand pit with sensors underneath, and the seabed, which is an underwater autonomous vehicle to probe the underwater environment. At the system level, these are the system level applications, the real world applications that we decided upon as the validating structure for what we were trying to do. So at the first one is 3D imaging of cellular structure with the goal of trying to understand the evolution of a mouse egg from basically the fusion of the cell towards the evolution of a healthy mouse. Can we actually map the evolution of that process? If we can, it would completely revolutionize the in vitro fertilization industry. The second is 4D image-guided therapy. Can you develop a way of, in real time, guiding a proton beam to hit the tumor and not the spine as the person is moving or breathing, because you do have to breathe, and you don't want that motion of the body to really destroy a part of the body that you're not trying to hit. The third is multimodal breast imaging, for the idea of really enhancing the reliability of breast cancer. The fourth is remote assessment of coral reefs under the water. And the fifth is underground assessment for buried waste. So let me just take one example, which is in fact the breast imaging example. The idea that we're going to use is we're going to use an emerging technology, which is CT, computer-aided technology, 3D imaging, which was developed at Mass General Hospital and with GE, We're going to fuse it with a number of different modalities: impedance imaging, optical imaging, microwave imaging, elastography. Fuse those, and the idea is to get a much more reliable prediction of breast cancer structure. So just in a nutshell, here's one of the examples of what we've done. In terms of the tomosynthesis itself, X-ray is giving you the structure of the breast region and the density variations within that region, including things that could be a tumor or could be just a benign growth. Optics, on the other hand, if you can get laser information into the breast region in a multiple sensor scenario, that will give you indication of blood flow, of the dynamics of the growth of the tumor. The problem with optics is when you send the optical signals into the breast, the signals scatter and it becomes a very diffuse region. And you can see up on the top here that if you did nothing, you have no information. The optics is just, smeared into the breast region. On the other hand, the concept of physics-based fusion says use the X-ray structure to determine how the photons scatter and reverse the path so that you can actually trace where the photons went and re-image the whole system. So we did that, and what you can see from that is that, in fact, you've now localized a tumor growth in the middle of the breast where before you had no information. The other aspect of this is the speed up. You can't take an hour because you're going to try and do radiotherapy or whatever on this region. You need to have almost real-time information. And what we've done in the center, again, is the image and data information processing. By implementing graphic processor units, we went from something like a 3-hour reconstruction to under 10 seconds using new GPU hardware. So that was a major breakthrough that now allows tomosynthesis to become a really almost like a standard treatment for breast cancer. And I know Lynn Preston was really excited about this. She was a survivor of breast cancer, and this became almost like an icon for our center. So what happens next? We were a process center. We developed a strategy of diverse problems, similar solutions. So the funding for the ERC ended. And, we were still working on some of the problems, but then Homeland Security announced a center competition to defeat explosive-related threats. Well, a tumor in the body, a bomb in a suitcase. There's no difference in terms of the tools that you can deploy in order to make progress in this whole different domain. And so we competed for this center. We had no knowledge of explosive-related threats. We had never worked with Homeland Security. We won. We won the competition. And again, this is your 3-level approach. Your grand challenge is comprehensive defense against explosive threats. There's no silver bullet. There needs to be cross-cutting research, and the outcome is fieldable products and systems. So basically, here is your 3-level approach, again, that really is a spin-off of the ERC to do essentially the same kind of processing, which is detecting anomalies, detecting things that could be threats to the security of the nation. And you can see that the 4 thrusts that we had, looking at explosive properties, looking at trace detection, bulk detection, signature analysis, validating test beds, leading to your grand challenges and fieldable technologies. That center ran for 12 years and is still running as an emeritus center. What's next? Homeland Security announced another center opportunity to look at the ways of protecting against soft targets. Churches, synagogues, schools, the horror show in Texas. How do we prevent or mitigate the impact of an attack on those soft targets? You can talk about a stadium. You can talk about July 4th celebration along the Charles River, where thousands of people gather, and all you need is a suicide bomber or an attacker to come into that venue, and you have chaos and disaster. So we, again, didn't really have a lot of experience in protecting soft targets. But we competed for this and we won. This is a newly formed center. It just started about 9 months ago. And again, the three-level approach is what gave us that edge in how do we create a systemic, transformative, and sustainable effort over a 10-year period. This is the 10-year center grant, by the way. And again, at the upper level, the goals are a soft target safety strategy, creating a platform which can be adapted to any soft target to mitigate and give situational awareness to stakeholders so that they can anticipate and mitigate the impact of an attack. And technology transition to the field is always there. At the fundamental level, 4 thrusts that really can create the synergy to allow you to get to the top level. We need facilities and case studies at the middle level. And again, the 3-level approach allowed for a strategic framework of an important problem that really related to how do you make a systemic impact. Finally, when I was immersed in the horror and the pain of the murder of George Floyd and the real concern about diversity and broad participation in this country, I decided to say, hey, can we take the 3-level approach and take it out of the technology development domain and bring it into other domains like the strategy of creating broad participation in engineering? How do we create a broad participation strategy so that when our grandchildren are in the workforce, they're in a workforce that is diverse and is really representative of our country? And so, NSF is one of the big ideas, created the Includes program. And the capstone program of the Includes initiative are the Includes Alliances. And so I said, let's go for an Includes Alliance, and put together a team and created the 3-level approach to the systemic goal. And the systemic goal in this case is in 5 years, we will have an annual graduation rate of 100,000 women and underrepresented minorities at the bachelor's level in engineering per year, and 30,000 per year at the master's and PhD level. That was the overarching system goal. And there were a number of other elements of the system level that are needed to achieve that goal. And then at the fundamental level, we have our key performance strategies and the building capacity level at the middle level, all of which is really coming together and showing how the NSF 3-level approach can be used to really grapple with almost any major societal problem. And so in summary, the 3-level method is extremely flexible. Students should and can use this approach for high-stakes materials such as their master's thesis, their PhD proposals, job applications, you name it. Students should be able to take this approach and apply it no matter how difficult the problem is. And so remember, so what? Who cares? Thank you.
Michael?
Yes.
You stole one of my questions. I am very intrigued that you applied the three-plane chart to broadening participation, and I'd like to explore that more at the roundtable. Congratulations for doing that. Excellent presentation. I'm a big fan of the three-plane chart, and you also folded in the DARPA questions in that mix. So great. Thank you so much.
You're quite welcome, Teresa. It was a pleasure.
Okay, see you at the roundtable.